Hi, I'm Kannan Lu. I'm a graduate student from UIUC. Today I'm going to talk about our recent progress on a family of magnetic materials, the intercalated transition metal dichalcogenides. This work is not possible without great support from the Oak Ridge National Lab, University of Tennessee, Knoxville, and NSF grants. The system I'm going to focus on is the so-called one-third intercalated transition metal dichalcogenides. The structure is shown here. This one-third basically means that the intercalates should occupy specific locations and form a hexagonal superlattice. As a result, the crystal structure breaks inversion symmetry and allow for an interaction called the Dichalcogenides interaction, DM interaction. This DM interaction can be casted into a cross-product form, and basically it tends to align to neighboring spins to be perpendicular. It is shown in one of these systems, chromium intercalated niobium sulfides. The spins of the intercalated chromium lie within the AB plane because of strong magneto-anisotropy, and couple ferromagnetic within the plane. These spins also couple ferromagnetic out of the plane in the presence of the DM interaction and the out-of-plane ferromagnetic coupling. The resultant ground state is a heliomagnetic state. The helical periodicity is set by the relative strength between the DM interaction and the ferromagnetic coupling. Planck plication of a field perpendicular to the helical axis ferromagnetic domain appears, and they are evenly separated by a topological 2-pi phase slip, known as a chiral magnetic soliton, which is actually a 1D skyrmion. The solitons form a lattice known as the chiral soliton lattice, and the spatial periodicity of this lattice can be tuned by the application of the fields. So the chiral soliton lattice is tunable potential for a conduction electron and is very promising in spintronics application. So how do we know if there's a chiral soliton lattice in this system? Well, there's a bulk character of this chiral soliton lattice, which has been shown in chromium niobium sulfides. So if you look at the magnetization versus temperature of this material, the chiral soliton lattice is manifested as a sharp cusp. And if you look at magnetization versus fields, the chiral soliton lattice is shown by slope changing behavior. The problem is, up to now, there's only one convincing example of soliton material. So what we are working on now is to expand this soliton material family. We started to look at these one-third intercalated transition metal dichalcogenides, which have actually been studied in the 70s. And it is generally believed that one gets ferromagnetic compounds if you intercalate vanadium, chromium, and manganese into the transition metal dichalcogenides. You get antiferromagnetic compounds if you intercalate cobalt and nickel. So the first set of material we look at is the vanadium intercalated transition metal dichalcogenides. I'll focus on this set of material from now on. We have grown single crystals of vanadium niobium sulfide and vanadium tantalum sulfide using iodine vapor transport method. The crystal we have are millimeter sized. We first tried to characterize the crystal symmetry by using single crystal diffraction. And because of twinning domains, usually the result is complicated and can be fit to both long central symmetric space group and the central symmetric space group. Notice that the long central symmetric space group is the correct space group to have DM interaction. So the single crystal diffraction is not the best way to discriminate the symmetry of the crystal. Then what is a better way to identify the symmetry of the samples? It turns out that in the case of chromium natrium sulfide, different symmetry of the crystal result in completely different magnetization behavior. It was shown that the ordered state, which is the non-central symmetric space group, has a transition temperature which is around 140 K. While if the intercalates occupy into wrong positions, then that basically means it's a central symmetric state, central symmetric symmetry, and the transition temperature is completely different, which is around 90 K. So we have also tried to dig out information from the magnetization. Shown here is the magnetization of 2 vanadium natrium sulfide samples. On the right is the corresponding powder X-ray diffraction. Right now, these 2 samples do not seem to have too much differences. But if we look closer, we'll see that one of the sample 2, has a clear high temperature magnetic transition. And correspondingly, we see the strength of 101 Bragg peak of sample 2 decreases. I want to emphasize that this is a real correlation. If we anneal the sample 2 again, such that the high temperature transition is suppressed, we see the 101 Bragg peak increases. So by comparing with the central symmetric space group, we know that the 101 Bragg peak is a signature for inversion symmetry breaking. So we associate the high temperature transition with the disordered case of the intercalates. We can actually make use of this correlation to several other similar compounds we made. Here's a list of transition temperatures that we think is a very efficient way to determine the symmetry of the crystal. You can come back to this slide if you need it. So we have now confirmed that the low temperature transition is resulting from the correct long central symmetric space group. The next question is, what's the magnetic structure of this phase? It was believed to be ferromagnetic, simply based on this magnetization data. But if we compare the magnetization of the ordered phase with, say, for example, a known ferromagnetic compound, manganese natrium sulfides, we see the magnetization of the vanadium compounds are just way too small. If we do a rough estimation, these magnetization data simply means that the moment is around 0.01 Bohr magneton per vanadium, which is way smaller than the spin-only moments. So we further used single crystal neutron scattering technique to determine the magnetic structure. At low temperatures, we see magnetic Bragg peaks rise on top of nuclear Bragg peak. Shown here is the pure magnetic Bragg peak 001. So this basically means that the magnetic structure is described by propagation vector k equals 0. We also track the intensity of 003 Bragg peak as a function of temperature. This can be regarded as an order parameter. And we are able to fit and extract the transition temperatures, and they're consistent with the magnetization measurements. We fitted the magnetic Bragg peak intensity to all possible models consistent with the k equals 0 magnetic structure. I will just show here the final results. So the best model consistent with the data is an A-type antiferromagnetic structure depicted in this plot. And the moment size is around 1.5 Bohr magneton for vanadium natrium sulfide and 1.37 Bohr magneton for vanadium tantalum sulfide per vanadium. You can also see the calculated intensity plotted against the observed intensity for all magnetic Bragg peaks observed. Random scattering around this 45-degree line is an indication of a good fit. Just to give you a sense of how bad models look like if the magnetic structure is completely ferromagnetic, then the calculated intensity do not match the observed intensity at all. So to summarize, we have determined the magnetic structure to be an A-type antiferromagnetic order, which is shown in this plot. This is completely different from previous literatures. The small net magnetization observed can be due to a very small out-of-plane canting of those moments. We've also talked about using 101 Bragg peak as a signature for determining the symmetry of the crystal. And we know usually in these systems, disordered intercalates results in different magnetization transitions. There's an open question though. We do not know what's the long wavelength structure as a result of competition between the antiferromagnetic order and the DME direction. At least within the instrument resolution, we have not seen any long-range chiral modulation. But that's the direction that we are looking into right now. I also want to mention that recently we have posted our paper into the archive. You can find that paper and look for details of the study from this link. So that's it, and thank you.